Sometimes it's the components we barely notice that are really doing the heavy lifting in our tech,
Definitely.
take the relay. On the surface, it seems simple enough, just an electrically operated switch. But when you kind of dig a little deeper,
Yeah.
you find this truly fundamental piece of engineering. And it's used in just an astonishing range of places.
Absolutely. And what's fascinating, I think, is how this seemingly basic device underpins so many complex systems.
Right.
So for this deep dive, our mission really is to get to grips with the core principles, what makes a relay tick, explore its diverse uses and understand why it's still so crucial even today with all our advanced tech.
And to do that, we've been diving into some really interesting material. We've got excerpts here from an engineering document. It's just titled RMELAS.pdf. Pretty straightforward.
Yep, gets right to the point.
Okay, so let's unpack this. The document emphasizes that the most common type, the one you'll see most often, is the electromechanical relay, or EMR. What's actually going on inside one of these?
Well, at its heart, the EMR uses electromagnetism. That's the interaction between electricity and magnetic fields, basically.
Okay.
You've got an energizing coil. Think of it as just wire wound around a permeable iron core.
Right, like a little electromagnet.
Exactly. And this core setup has a fixed part, they call it the yoke, and then there's a movable part, the armature. And that armature is held in place by a spring.
Right, so it's like a tiny magnetic tug-of-war is set up inside the device. When we send a low-voltage signal, AC or DC it says here, to that coil, what happens then?
Well, that current flowing through the coil creates a magnetic flux, a magnetic field.
Okay.
And this field generates a mechanical pulling force. It's strong enough to overcome that spring's resistance, and it physically moves the armature.
Ah, okay.
And here's where it gets really interesting. This movement, this physical movement of the armature, is what operates the electrical contacts inside the relay.
And those contacts are what actually do the switching job in a different electrical pathway, right?
Yeah, precisely. They either close, which completes a separate circuit, or they open, which breaks it. And one of the key benefits here, the document really points this out, is the electrical isolation.
Yeah.
The control circuit, the one powering the coil, is completely separate, electrically isolated from the circuit being controlled by those contacts.
That makes total sense. Keeps things safe, stops electrical noise, jumping between circuits, that kind of thing. Now, you mentioned a spring. What's its job in all this?
The spring is crucial. It's what returns the relay to its original state. When you turn the current to the coil, OFF, right, the magnetic field collapses.
Yeah.
And the spring just pulls the armature back to its starting position, its rest position. And that, in turn, resets the electrical contacts to however they were initially.
So electromagnetic force, then mechanical movement, which connects or disconnects other circuits. Simple but effective. Now, the document talks about normally open and normally closed contacts.
Right.
What do those terms actually mean in practice?
Good question. This refers to the state of the contacts when the relay coil is de-energized. When the relay is just sitting there, turned off.
Okay, the default state.
Exactly. Normally open, and no contacts, sometimes called make contacts, they're open in this state. No connection.
Right.
When you energize the coil and the relay switches on, these contacts close. They make the connection, completing the circuit.
Okay, so normally open means the path is broken until you power the relay. Makes sense. What about normally closed, or NC contacts then?
Normally closed or break contacts are just the opposite. When the relay is off, coil de-energized, these contacts are already closed. Current can flow.
Okay.
Then when you energize the coil and the relay switches, these NC contacts open, breaking the circuit.
Got it. So it's all about that default setting, when the relay isn't actively doing anything. Now, the document then mentions changeover contacts. What extra capability do these bring to the table?
Right, changeover, or CO, also called double throw, DT. The document mentions Form C, or transfer contacts, too. Lots of names for the same basic idea.
Okay.
These take things a step further. They're more versatile. What's kind of cool here is that they essentially combine both a normally open and a normally closed contact, but they share a single common terminal.
Interesting.
So when the relay switches, one circuit is broken at the same time as the other one is made. It transfers the connection. And the document specifically mentions Form C contacts use a break before make action.
Break before make. Okay, that sounds important. Why?
Well, it means the existing connection is definitely broken before the new one is established. This prevents any possibility of momentarily shorting the two circuits together during the switchover, which could be bad news in sensitive systems.
Right, avoids accidental connections.
Yeah.
Makes sense. The document also briefly mentions Form D contacts. How are they different?
Form D are less common, but they do the opposite, make before break. The new connection is made before the old one is broken. This can be useful in specific situations where you absolutely need to maintain a continuous circuit, even for that tiny instant during switching.
Okay, so different tools for different jobs there. We're getting a clear picture of these contact types. Now, the document gets into the terminology of poles and throws. This sounds like it describes how many circuits the relay can handle, right? Can you break that down for us?
Absolutely. It sounds a bit technical, but it's pretty logical once you grasp it. Pole just refers to the number of independent circuits the relay can switch. Think of it like how many separate switches are inside that one relay body, all controlled together.
Okay, number of circuits.
And throw refers to the number of positions each of those poles can connect to. Can it just connect to one other point, single throw, or can it switch between 2 points, double throw?
Right.
The key takeaway here really is the flexibility this offers engineers. You can control multiple independent things or route signals in complex ways, all from one single control input to the relay coil.
So let's start simple. SPST. What does that tell us? The doc says 2 terminals disconnected, plus the coil, so 4 terminals total.
Exactly. SPST is single pole, single throw, one circuit being switched, single pole, and it can either connect to one other terminal or be disconnected, single throw, like a basic on-off switch.
Simple enough.
But the document rightly points out, just saying SPST doesn't tell you if it's normally open or normally closed. It's ambiguous.
Oh, right.
That's why you sometimes see the more specific terms, SPNO for single pole normally open and SPNC for single pole normally closed. Much clearer.
Definitely better for clarity. Okay, what about SPDT? Document says a common terminal connecting to either 2 others. 5 terminals total, including the coil.
SPDT is single pole double throw. Still one circuit being switched, single pole, but now it can connect to one of 2 other terminals, double throw. That common terminal is the key. It gets switched between the other 2 contacts.
Okay.
It's basically that changeover function we just talked about, but for a single circuit path.
Right, like a little electrical seesaw for one circuit. Okay, moving up. DPST, double pole, single throw. The doc says this is like having 2 SPST switches in one package. 6 terminals total.
Precisely. DPST means 2 independent circuits are being switched simultaneously, double pole, and each of those circuits can either be connected or disconnected, single throw. So 2 separate on-off switches controlled together.
Gotcha.
And importantly, as the document notes, each of those poles could be Form A, which is normally open, or Form B, normally closed. So you get flexibility in how those 2 circuits behave by default.
Okay, like 2 separate light switches on the same handle, kinda. And finally, DPDT, double pole, double throw. 8 terminals here, likened to 2 SPDTs in one.
That's the one, DPDT. 2 independent circuits being switched, double pole, and each of those circuits can be switched between 2 different connections, double throw. So you've got 2 separate changeover switches, all activated by that single relay coil.
Wow, okay.
It really builds up.
And the document mentions you can even scale this further, like 4 PDT would be 4 independent double throw switches controlled together. That gives you a huge amount of switching power from just one control signal.
Exactly. Massive control capability.
Now let's talk about something the document calls usage considerations, specifically protecting the control circuit itself. It mentions something called back EMF. What is that, and why is it something we need to worry about?
Ah, yes, back EMF. This is a really important practical point for anyone actually designing circuits with relays.
Okay.
See, when current flows through that relay coil, it builds up a magnetic field, right? That's how it works. But when you suddenly turn that current off, the magnetic field doesn't just, like, instantly vanish, it collapses.
Right.
And this collapsing magnetic field actually induces a voltage back across the coil, but in the reverse direction. That's the back EMF, back electromotive force.
And this reverse voltage,
Yeah.
it can cause problems for other components.
Oh, absolutely. Big problems, potentially. The document highlights that this induced voltage spike can be very high, much, much higher than the voltage you used to switch the relay on in the first place.
Yikes.
And this high reverse voltage can easily damage sensitive semiconductor devices, things like transistors, microcontrollers, that are often used to actually switch the relay coil on and off.
Ouch. So how do engineers protect these delicate components? The document mentions using a reverse bias diode,
Yeah, that's the standard, most common solution. It's really quite neat. You connect a simple diode across the relay coil terminals, but you connect it in reverse bias.
meaning it normally doesn't conduct current.
Exactly. In normal operation, when the relay is on, the diode does nothing. But when you turn the relay off and that back EMF spike occurs, the reverse voltage is now in the forward direction for the diode.
Ah, so the diode suddenly turns on.
Precisely. It starts conducting. It basically provides a safe path, a short circuit, for that induced current to flow through.
So the diode essentially soaks up that excess energy from the collapsing field.
You got it. It lets the stored energy in the magnetic field dissipate harmlessly as a small current flowing through the diode itself, preventing that damaging high-voltage spike from ever reaching the sensitive control components. It's often called a flywheel diode or freewheeling diode or flyback diode, different names, same job here.
That's a really elegant solution. Just a simple diode saving expensive components.
It's clever, isn't it? Basic electronics doing a crucial job.
The document also briefly mentions other protective things like RC snubber networks, MOVs, Zener diodes. We don't need to dive deep into those, but good to know there are other options for handling these voltage spikes.
Yeah, different tools for different scenarios, essentially.
Okay, now let's get to the really fascinating part, applications. The document lists a huge variety of uses. One of the first it mentions is amplifying digital signals or switching large amounts of power using only a small operating power. Can you give us some solid examples of that?
Certainly, think way back to the early telegraph systems. Telegraph relays were absolutely crucial.
How so?
Well, signals would get weak traveling over long wires. So a weak incoming current would be just enough to trigger a relay. That relay would then use its own local power source to send out a fresh, strong signal down the next leg of the wire. It regenerated the signal.
Oh, like a signal booster.
Exactly. And then controlling high voltage circuits with low voltage signals, that's a huge application, mainly for safety and control convenience. The document mentions things like some older modems used relays for switching lines, and even today in some high-end audio amplifiers.
Audio amplifiers. Why relays there?
They're often preferred for switching the actual audio signal paths because they provide a really clean physical break. No semiconductor junction messing with the signal purity. Purists like that.
Interesting. And what about controlling high currents with low currents?
The perfect example, one most people have interacted with without realizing, is the starter solenoid in your car.
Right. The click you hear before the engine cranks.
That's it. You turn the key, that sends a small current from your ignition switch to the relay, the solenoid. That relay then closes a very heavy-duty contact, connecting the massive current directly from the car battery to the starter motor. Way too much current to route through your ignition switch.
That's a fantastic everyday example. Okay, the document also highlights a really critical role, protecting power transmission and distribution lines. How do relays work there?
In the power industry, they're called protection relays, and they are absolutely vital. They're like the intelligent watchdogs of the grid.
Watchdogs.
Yeah, they constantly monitor the current and voltage on the big power lines. If they detect a fault condition like a short circuit or a massive overload, maybe a tree falls on the line.
Right, something bad.
Something that could cause major damage or blackouts, these protection relays instantly detect it. They then send a signal to trip the main circuit breakers, opening the circuit and isolating the faulty section of the line.
So they prevent a local problem from cascading and taking down a whole area.
Exactly. They contain the fault, protect expensive equipment, and maintain stability on the rest of the grid. They really are guardians of our power supply.
Wow. Okay, another key application mentioned is that isolation thing again, separating controlling circuits from controlled circuits that might be at very different voltage levels. Why is that so important?
Well, it comes back to that fundamental safety benefit we touched on earlier. Imagine you have a simple low-voltage light switch on the wall, maybe controlling a powerful mains-powered heater or motor.
Okay.
The relay acts as that crucial safety barrier. It ensures the high voltage, the mains electricity in the heater circuit, is completely physically isolated from the low-voltage wiring going to the switch you actually touch. Protects the user from electric shock. It's fundamental for safety regulations.
Absolutely essential. Can't argue with that. Now, this next part is particularly intriguing, using relays to implement logic functions. The document explains you can actually build Boolean logic A and D, that kind of thing, using clever arrangements of relay contacts. How on earth does that work?
It's actually quite ingenious, and it's how the earliest computers worked. Think about an A and D gate. You need output C to be true only if input A and input B are true, right?
Right.
You can do that by connecting two normally open relay contacts in series. Let input A control one relay, input B control the other. Current can only flow through the whole series chain, giving you output C if both relays are energized, closing both sets of contacts.
Ah, I see. Both switches have to be closed. Makes sense. What about an OR gate? A or B or both?
For OR, you connect the normally open contacts in parallel. If relay A or relay B or both are energized, their contacts close, completing a path for the current. So the output is true if A or B is true.
That's pretty neat. Very visual. What about the XOR gate the document mentions? Using changeover or form C contacts. That sounds more complex.
It's a bit more clever. XOR means true if A or B is true, but not if both are true. You can achieve that by using those changeover contacts, wiring up both the normally open and the normally closed path in a specific way across two relays. It creates a circuit that only passes current under the exact XOR conditions. Wow.
And the document also mentions that ladder logic, that graphical programming language often used for industrial controllers, PLCs, and things.
Yeah, I've heard of that.
Its structure is actually based on these relay logic diagrams. It comes directly from that history.
It's mind-blowing to think these mechanical switches could form the building blocks of computation. And speaking of that, the document touches on the historical significance relays in the earliest digital computers, before vacuum tubes really took over, let alone transistors.
Oh, absolutely. This really highlights the spirit of those early pioneers. Relays were the workhorses. Machines like the ARA, the Harvard Mark II, the Zeus Z2 and Z3 computers. They were built using thousands, sometimes tens of thousands, of clicking electromechanical relays.
Imagine the noise.
Exactly. Huge racks of these things clicking away, performing calculations. They were the active switching elements, doing the binary logic, storing bits of information. Of course, they were slow, bulky, power-hungry compared to later tech.
Yeah, massively so, I bet. But they were absolutely essential. They were the dawn of the digital age. It really puts the progress we've made with semiconductors into perspective when you think about a room-sized relay computer versus the phone in your pocket.
It's incredible. Now, the document also points out something really interesting. Relays still have a critical role in safety-critical logic, especially in places with nuclear radiation, where semiconductors can be unreliable. Why is that?
That's a key point. Semiconductors, transistors, and integrated circuits, they're quite vulnerable to the effects of high levels of ionizing radiation. It can cause errors, malfunctions, even permanent damage.
Okay.
Relays, being electromechanical, are inherently much, much more resistant to those radiation effects. Their operation depends on magnetism and physical movement, not delicate silicon junctions.
So they just keep working.
Pretty much. This makes them absolutely vital in applications where failure is just not an option and radiation is present. The document mentions things like control systems for machinery handling radioactive waste. You need absolute reliability there.
That's a really compelling reason for them sticking around in those specialized high-stakes environments. Okay, the document then discusses how relays can be modified to provide time delay functions. How do you make a switch wait before it flips?
Yeah, you can build delays right into the relay mechanism itself, which is quite clever. For short delays, like a fraction of a second up to maybe a few seconds, you can use a copper disc or slug fitted near the coil and armature. When the coil de-energizes, the collapsing field induces eddy currents in this copper. These currents create their own temporary magnetic field that opposes the change, slowing down the release of the armature.
Like a magnetic brake.
Kind of, yeah. For longer delays, maybe up to a minute or so, they used to use dashpots.
Dashpots, like on screen doors.
Exactly the same principle. A small piston moving through oil or air inside a cylinder. It physically slows down the movement of the armature or the contact mechanism.
Okay, mechanical damping.
Right. And for even longer delays, you could integrate a mechanical clockwork timer mechanism directly with the relay. Wind it up, and it trips the relay after a set time.
Wow, clockwork relays. So you can really fine-tune the timing just using mechanics and basic physics?
Yep, lots of ingenuity there.
The document also mentions some very practical everyday applications, like vehicle battery isolation and switching to standby power.
Yes. Absolutely. In vehicles like RVs, boats, 4WDs, things that often have a main starting battery and a separate house or auxiliary battery for running lights, fridges, etc.
Right?
A heavy-duty relay, often called a battery isolator or voltage-sensitive relay, VSR,
Mm.
is used. It automatically connects the batteries together when the engine is running, so the alternator charges both, but disconnects them when the engine is off.
So you don't accidentally drain your starting battery running the fridge overnight.
Precisely. Prevents that dreaded flat battery in the morning. And in critical systems, hospitals, data centers, industrial processes, relays are essential for automatically switching over to a backup generator or UPS. A standby power supply, if the main grid power fails, ensures continuous operation.
It's truly remarkable just seeing how many diverse applications rely on this seemingly simple component. From the very dawn of computing, power grid safety, our cars.
Yeah.
The relay is just everywhere when you start looking.
Absolutely. What's really striking is how this fundamental electromechanical principle, turning electricity into magnetism, into motion, has been adapted and refined well over a century now to serve such an incredibly wide array of needs. It really underscores the enduring relevance of understanding even these basic building blocks.
So as we bring this deep dive into relays to a close, it's crystal clear that despite their, relatively straightforward design, they are anything but insignificant. We've explored how they function as these electromechanical switches, the crucial differences between normally open, normally closed contacts, the amazing versatility of changeover contacts, how poles and throws define their switching capabilities, the vital role of protection like that slywheel diode, and their just surprisingly vast range of applications, from the earliest computers all the way to protecting our modern power grid.
Which really leads to a final thought, perhaps, for you, the listener. Now that you have this hopefully deeper understanding of how relays work and the incredible range of jobs they do, where else might you encounter them in your daily life? Things you hadn't maybe considered before. And maybe what future innovations might still build upon these fundamental electromechanical principles. It's worth thinking about how even simple-seeming technologies underpin so much around us, isn't it? Makes you appreciate the ingenuity involved.